Professor Bialis here. In this video, we're going to be talking about section 7.4. Back in 7.3, we talked about just some introduction of adding and subtracting rational expressions. How to add them when they have a common denominator, how to identify what the common denominator is, and how to build a new equivalent fraction with a given denominator. What we're going to do in this section is combine all three of those ideas in each separate problem. Okay, so there's not much background information that we need to go through. We've already gone through that. We're just going to jump right into some examples. So let's see how this plays out. We are going to add y over 5. Actually, we're going to subtract in this case. And then 3y over 15. Okay, now always identify what type of problem you are dealing with. Whether it's math or just life in general, we need to know that there is a problem and what type of problem it is before we can fix it or work through it. Okay, so in this case, we're dealing with subtraction. When we do subtraction, first thing I want you to get in the habit of doing is changing it to addition and attach that minus sign to something. Most of the time, it's going to be that numerator. I'll show you an example in a few minutes where the denominator is going to be a little more helpful. Okay, so now we're addition at this point, but same rule applies. We need a common denominator. Okay, so first of all, we need to identify what that denominator is. Between a 5 and a 15, the LCD should be a 15. Okay, this fraction already has it, so we can just carry it down. This first fraction, we need to make this into an equivalent version with a 15. We did that last section. So I'm going to multiply bottom by 3 and the top by 3. Remember, 3 over 3 is a 1. That's why I'm multiplying top and bottom. So I've got 3y. After that, since the common denominator is there, I just add across the numerator. 3y minus 3y is 0, which is a 0. That's it. As you can see, we did all three components of the last section in one. We added with like denominators. We had to identify what the LCD is. And then we took a fraction and built an equivalent form with a certain denominator we were looking for. Okay, all of that rolled into one. Now, what I want you guys to realize with this problem is you did have another option to go through it. Let me show you what I mean. Okay, again, switch that, and we're here. Okay, remember the key is we need a common denominator. Why we need a common denominator is to make sure that we're adding like pieces. If I have a pie and I have a piece like this and I have a piece like this, let's say this and this, I don't want to add those and say I have two pieces. That's not the same. They're not the same size. Okay, or if I have a $1 bill and I have a $5 bill, I don't want to say, well, I have two bills. Okay, there's a value underlying there. Same thing here. I want the value to be the same. So, to make these the same, typically we build one up, or maybe both of them up. But what we can sometimes do, not often, but it is possible, couldn't I reduce this? And then by doing that, they match. Okay, so y minus y is still a 0, and I get my 0. Same result. So again, most of the time, 99.9% of the time, we're going to have to build these up like we did here with multiplication. But it is possible, if that reducing will help you match those denominators, go for it. That's not going to hurt anything if you go about it that way. Okay. Typically though, when you reduce, they don't match up, so you have to build them back up anyways. But just keep that in your back pocket as an option. Let's look at another one. Let's say we've got that. Okay, so again, we're adding, so we have to think, what do we need in order to add? We need a common denominator. What would that denominator be? You have an 8 and a 10. Let's look at the numbers first. Between 8 and 10, let's think about a 10. 10, 8 doesn't go into that. 20, 8 doesn't go into that. 30, no. 40 works. 40 would be the numerical portion of the LCD. And then we have x's. Now remember, when we deal with an LCD, and there's exponents involved, we're going to be looking at the biggest exponent we have. So there's an x in the mix, and the biggest exponent on the x is a 2. So that goes into our LCD. So again, let me go through that again. There's an x in the mix, so we need that in there. And the highest exponent on the x is an x squared. Okay, so write down whatever's in the mix, and then if there's an exponent anywhere, you take the highest one. Now we need these to become this. So 8 times a 5, and then I need 2 x's, but I only have 1, so I'm going to throw another x in there. 5x times 5 is 25x. Here, the x squared's already matched, but a 10 needs to be a 40. So I'm going to multiply by 4, and I've got 44. Okay? What I basically did is unreduce the problem. I cut it into smaller pieces, so to speak, so I can have more opportunities to work with it. Now they're the same size piece, so I add across the top. Now notice those are not like terms. So best I could do is that, and I carry that denominator down. That's all there is to it. Okay? Let's go to another one. Okay, so for this, same as before, get in the habit, put that on there, just so I don't lose it hanging out in the middle. After that, I'm going to have to decide what the LCD is. Remember when we were trying to decide what the LCD is, we always want to factor first to see really what are the components of that denominator. So this, I'm going to factor as an x plus 3, x minus 3. I'm going to cross that out because I don't want to look at that anymore. These are my denominators, okay? So my LCD, whenever we have quantities like this, I'm listing what's there. What is there? I've got an x plus 3, I have an x minus 3, and I already have the x plus 3 in the mix. So there's my LCD. Okay? Now the first fraction already has that, so I'm just going to bring that 10x down. This one is missing the x minus 3, so I'm going to throw that in the denominator. But if I throw it in the bottom, I throw it in the top. And I got negative 5x plus 15. Okay? Now, notice I didn't distribute into this. I did distribute there. Okay? I distribute in the numerator because the next step is to combine like terms. I need it distributed in order to do that. So what I get, 10 minus 5 is a 5x plus 15. I did not distribute the denominator because after I pull it together, what's my next phase? I need to possibly reduce that thing. So I need to factor and then reduce. So that's why I don't distribute this, but I do distribute that. Okay? And one more thing, it's 10 minus 5 giving me the 5. I didn't just drop the negative. Okay? Once I get to this, I do any factoring that's possible. And then once I factor, those are gone. And what I'm left with is that. And there we go. Okay? Okay, so again, I'm adding. That means I need a common denominator. So I'm going to give myself a place to go, and then I need to build that common denominator. Remember, you list what you have. Please be careful. This x and this x are very different because this is that x plus 1. Okay? So what do I have in the mix? I see a 7, I see an x, I see an x plus 1. Those are all the different components that are there. And then I'm going to list that here as well. Okay? Now, I need to build that. I need to make that happen. So I have the 7x. I'm missing the x plus 1. If I put it on the bottom, I put it on the top. I distribute that 5. I now have an equivalent fraction. Over here, what am I missing? I'm missing the 7x. Put it on the bottom, put it on the top. 2 times 7x is 14x. After that, combine those like terms. And we have that. There's nothing to factor here. There's nothing that reduces. We're good to go. You're going to notice in a lot of these problems that I keep saying the same thing again and again and again. You should be doing the same thing at home. It doesn't mean you have to say it out loud. If you can, that's better. But at least in your head, you should be thinking and saying the same thing. You want this to be a repetition. You want this to be a routine. Okay, that doesn't mean that you're cheapening anything about this. Okay, that's what this is. This is a routine. Okay, driving is a very important, very complicated task, but it's a very routine task. You don't think about where my key goes, where's my turn signal. It just automatically happens. And once you do that, you can problem solve with what's in front of you. Same thing here. Okay, this is a routine task, and we want to get this down, this tool down, this routine down, so that when we get into an application, we don't have to think about this. The setup is important, and then it's like, okay, we can just solve, no big deal. Okay, that's where we want to get to. But a lot of people you set up an equation, you say solve it, I don't know what to do. Okay, so that's why we need to be able to get this skill before we can get into the application. Let's look at a couple more of these. How about okay, now this is one of those situations where we can tweak our approach a little bit. Normally I say, make a routine out of it, or a habit out of it, put the negative on the top. However, look at those denominators for a second. They don't match. But we saw an example like this in the last section, where we can make the match if we factor out a negative. The negative is what makes the match. We don't really need to factor one out though, if we already have one to use. Remember, the negative can distribute on the top or the bottom. I'm going to put it on the bottom. And now they match. I don't need to do any work to make those denominators match. And I could just say 10 plus 15 is 25. I like putting the x first, so I'm going to write it like this. And there's nothing more to it than that. Okay, so again, 99% of the time, I'm distributing that negative on the numerator. Unless distributing it on the denominator makes the match, or makes it flip like you want it to flip. Okay, you don't have to factor a negative out if there's one that you can put in there waiting for you. Okay, so let's look at another one. Okay. Now this one's different because yes, it's a rational expression, but we don't have fractions all through. Okay. That doesn't mean that we're stuck with that. Okay. Remember, a rational number, a rational expression is something that can be written as a fraction. Just like that. Okay. I really suggest don't try and just work with it as a 2 because 2 is a lot nicer. It is, but we need fractions. We need to work with those denominators. So put a denominator on there. Now, remember we're adding, so we need to decide what the LCD is. In this case, it's that x plus 5, like so. Okay, this already has it, so I just bring it down. This is missing the x plus 5, so I put it in the top and the bottom, and then I distribute that too. So I've got 2x plus 10. And after that, combine like terms. 3x plus 10, x plus 5. There's nothing to factor, nothing to reduce. We're good to go. The key to this problem is introducing that fraction on something like that. Even if this is a polynomial, put a 1 under it so you have that fraction to work with throughout all the terms. Okay? How about this one? Okay, so a few adjustments right off the bat. Put that on there so I don't lose it. After that, there's some factoring that can be done in those denominators. Don't just say, well, I got this quantity and this quantity. Maybe there's something they have in common, so we don't want to double up on it. So what I have is an x out of here, and here I can take a 2, a 4, and now those are gone. If it makes you feel better to rewrite the whole thing, go ahead. It's not necessary though. Now, as you can see, there is a common factor there, so we don't want to double up on that. If you keep this as is, and then you try to pull it together with the LCD, sometimes you create something that you can't factor. You need to factor it, but you can't factor it using basic methods. So that's why we want to keep it as simple and as broken up as we possibly can. Now, let's build that LCD. So I see an x in the mix. I see a 3x plus 2 in the mix. I see a 4. I'm going to put that out in front. And then I already have the 3x plus 2. So there's my LCD. And again, all I did was say, what do I see? I didn't try and do anything fancy. Just I listed what's in there. Now, what am I missing out of this? I'm missing a 4. So I'm going to put that in the bottom, put that in the top. So I get 4 times 4 is 16. What am I missing here? I'm missing an x. So I get negative 3x squared. Okay, so I factored, decided what my LCD is, and then I built equivalent fractions with that common denominator. At this point, combine. So I get 16 minus 3x squared, since those aren't like terms, that's the best I got. And then I have a 4x, 3x plus 2. And that's it. You could factor out a negative to put the x squared in front, but that doesn't really allow for anything else after that. So honestly, I would just leave it as this and move on to the next one. Okay, let's do one more example. Okay, so again, we're adding, so we need a common denominator. In order to get the common denominator, we need to factor, so let's do that. Now, with this trinomial here, we get x plus 2, x plus 2. That would be what it would look like if you're using guess and check. However, I said it back in chapter 6 that if you start writing things like this, I would stop and change it to that. This is the reason why I said that. Because remember, when we find an LCD, the highest exponent needs to be carried through. If you don't have that square there, it's likely that you're going to mess something up along the way with finding your LCD. Put exponents on things. Don't leave them separate. Not that it's wrong, but we're going to miss something along the way. Okay? So write this as an x plus 2 squared. This then is x plus 2, x minus 2. And those are my two denominators. Now, what is my LCD? I see an x plus 2, I see an x minus 2, but the highest exponent on x plus 2 is a square. If I didn't have that, if I had those separate, in all likelihood, you're probably not going to put that square on there, and that's a necessity in this case. Because there were 2 in one shot, you need to have 2 in both. Okay, so I copy that over. And we have that. Okay? So again, exponents are important. Don't write it separately, put the exponents where they belong. Now what's missing here? That x minus 2 on bottom and on top. Distribute to get a 6x squared minus 12x. What's missing here is this square. We can't just square though. We're going to multiply by another x plus 2. And that'll give you the x plus 2 squared. I then distribute, and there we go. Now the next phase is to simply pull all this together. So we have a 7x squared minus 10x. And then we have x plus 2 squared, x minus 2, and there we go. Now, one thing to realize here is this numerator, that can be factored. Okay, so when we do that, we can take an x out. Oops. And we have this. Now, one thing I want to point out with this, I factored, but did that allow me to reduce anything? Not really. Okay, so if that's the case, this is also an acceptable answer. However, this is better. We want to lay things out, okay, as much as we possibly can to show, see, there's nothing else I can do. This is okay because there was nothing to really reduce, but always try and factor. I get students who say, well, I'm looking at it, if I factor, it's not going to help, so I'm just not going to factor. And they miss something and it would have helped, it would have reduced. So always factor so you can see for a fact there's nothing else that can reduce, or maybe there is something that can reduce and you can get the correct answer. Always think about factoring at the end of an addition and subtraction problem, okay? So that's pretty much it. There was really no new information in this section. It was just compiling all the different components of the previous section. This, as always, is something you need to drill, drill, drill. Okay, talk yourself through it. Make your own sayings and script to help you be very consistent through each of these problems. Okay, as always, work hard. Let me know if you have any questions, and I'll see you next time.